We talked at the beginning of this chapter about empirical formulas and molecular formulas, right? And we said empirical formulas can be determined from experimental information. So you can figure out what the empirical formula is from elemental analysis. This is where you may take the compound and decompose it and measure the masses of the elements that were in it. Or you can measure masses of elements that react to combine and make that compound. We're going to do that in experiment 3A. You can also calculate the empirical from percent composition. It's important to remember that the empirical formula gives us the ratio of atoms or the ratio of moles of atoms, not the ratio of masses. So these are the steps for finding an empirical formula. You want to start out with the mass of each element present in a sample of the compound. If they give you percentages, then you assume 100 grams to make things easy for yourself, and then the percentage is the same number as the number of grams. Okay? So you get that info, and then you're going to take those masses and convert them to moles, because we need to look at the ratio of moles, not the ratio of masses. Then we're going to get mole ratios. We're going to take the smallest number of moles, divide everything by the smallest number. In the book, they write out, kind of a formula with formula subscripts. Personally, I think that's stupid, but whatever. He must know something because he's been very successful. We need to be a little bit careful here with rounding because there's going to be error in the measurements, and so we're not expecting these numbers to come out perfectly, but how close is close enough? This is my rule of thumb. If you're within 0.2 of a whole number, you could round it. So if you come up with a ratio that's 1.91, well, that's only 0.09 away from 2. You could round that up to 2. Or if you had 1.80, that's kind of like right on the line. Or 2.20, you could round that to 2. But if you have 2.25, you can't round that to 2. Okay? If you can't round things to whole numbers, then you're going to multiply all of them by the same whole number until you get whole numbers. So a lot of us recognize that 0.5 is the same as 1/2. So if your number is something 0.5 and you multiply it by 2, you're going to get a whole number. So you can recognize the fractional equivalence of, or the decimal equivalence of the fractions like 1/3, 1/2, etc. Or you can do trial and error. Try multiplying by 2. If that doesn't work, try 3. If that doesn't work, try 4. Usually that's all it takes. So we're going to do an example. I'm going to skip that one, but I'm going to do this one. Ibuprofen, here it is again, has the following mass percent composition. What's the empirical formula? So the first step is to find the masses of the elements. They didn't give us the masses, they gave us the percentages. So we're going to choose 100 grams. Because if I have 100 grams, then 75.69 grams is carbon. So I just take those percentages and I write them down as grams. 75.69 grams of carbon, 8.80 grams of hydrogen, and 15.51 grams of oxygen. Convert to moles. So I want to go grams of carbon to moles of carbon. And so that's going to involve the molar mass of carbon. So what about sig figs? Like, we don't care about sig figs. Well, sometimes you have to. What's going to happen here is we're going to end up with whole numbers. So exactly how many sig figs we keep doesn't matter, but we want to keep enough that it doesn't mess up our answer. If you keep 4, you should be fine. So I'm not even going to put down extra digits. I'm just going to write down 4. So that's how many moles of carbon would be in that. Hydrogen, 1 mole of hydrogen is 1.008 grams. 8.8 divided by 1.008 equals 8.730 moles of hydrogen. And oxygen, we're going to be converting between grams and moles like nonstop. 15.51 divided by 16. So what your book would do is it would say, well, these are my tentative subscripts. Carbon would be 6.302 moles. No, I'm sorry, not yet. I did this yesterday too. We have to find the ratio first. So we're going to look at these numbers and we're going to find the smallest one. We're going to do that because if we divide by the smallest, all of our ratios will be 1 or greater, and the subscripts all have to be 1 or greater. So we're going to divide by the smallest. So one of them always ends up being exactly 1. Let's see, 8.73 divided by 0.9694. So this comes out to be 9.006. And this comes out to be 6.501. So this is good. We can round that to 9. This is good. That's a whole number. That's 1. But this is 6.5. In an empirical formula, if we had a subscript of 6.5, that would tell us there's 6.5 atoms in the molecule. You can't have half an atom. It has to be whole numbers. So let's see what happens if we just multiply by 2. So I take that number and I multiply by 2. I get 13.00. And so that one times 2 is 18.01, and this one times 2 is 2. So here I did not get a whole number, so I multiplied them all by 2. That works because this is 6.5. If this was 6.75, I'd need to multiply by 4 to get the whole number. So these then are the subscripts for the empirical formula. And we don't need to worry about which one should we write first. Use the same order that they gave them to you in the problem. C13, H18O2. This is an empirical formula because 13 to 18 to 2 is the lowest whole number ratio. So there we go. How do we find the molecular formula? The molecular formula is going to be some multiple of the empirical formula. Sometimes that multiple is 1 and they are the same thing. In order to find the molecular formula, we need one more piece of information. We need the molar mass of the compound. In problems, that has to be given to you. So what we want to find out is how many times bigger is the actual molecular formula. So we're going to take the molar mass and divide by the mass of the empirical formula. That's going to give us a whole number. And that's going to tell us what to multiply the subscripts of the empirical formula by. So let's do an example. Compound has an empirical formula CH and a molar mass of 78.11 grams per mole. What is its molecular formula? Well, it's going to be C something, H the same something, but how do we figure that out? Well, to find that multiple, I'm going to take the molar mass that they gave me, 78.11 grams per mole, and I'm going to divide it by the molar mass of the empirical formula, which you just calculate. .11 divided by 13.018 equals 6.000. That tells me that the molecular formula is 6 times heavier than the empirical formula, which it means it has 6 times as many carbons, 6 times as many hydrogens. This is not how you would write the answer, but it can help you to see what are we doing. I've got that empirical formula and I'm multiplying by 6. And so as a result, I'm going to get C6, H6 as my molecular formula. And then you can double check that by calculating the molar mass of that, and it should match up really, really close to that one.
For the test, are we going to have to remember the multiple by for the subscripts?
There will be a question on the exam, or you have to calculate the empirical formula.
So we have to memorize the actual what we multiply the subscripts by, right?
Well, no, you don't have to do that. The trial and error method actually works pretty well. So if you get ratios that aren't whole numbers, try multiplying by 2. Start with the one that isn't a whole number. Multiply it by 2. Is that within 0.2 of a whole number that you can round it off to? Great, you're done. If it isn't, multiply by 3. If that doesn't work, multiply by 4. And I really don't imagine a problem going past that.
Okay.
So that's a lot simpler than trying to memorize all those fractions and the multipliers. Yeah, your brain can only hold so much, and you want to save that space for the stuff you really need. Any other questions? Combustion analysis. Okay, so this is related to finding the empirical formula, and it's sort of more practical, but we're also not going to use it after this chapter. So I'm going to talk to you about it. I'm not going to work out the example. There is a problem like this on the worksheet. There probably will be a problem on the exam, but I won't make it the hard kind. And so later today, I am going to record a video of the worked example and put that on Canvas so that you can watch that. If you're struggling and you're looking for things that you can skip, I give you permission to skip the combustion analysis kind of problem, okay? It's just not that important. But anyway, here we go. So how do they figure out empirical formulas? One way, for hydrocarbons or anything that's carbon, hydrogen, and oxygen, you can burn that substance in a confined space, and you can catch the products, the gas products that come out, and you can figure out what the empirical formula is that way. So let's look at this illustration. So you measure a sample. You could do this with a peanut, or this is how they actually find. I take that back. That's something else. Never mind. You're going to put it in this furnace. You know its mass. Oxygen's passed through here, and so this burns. All of the carbon becomes carbon dioxide. All of the hydrogen becomes water in the gas state. Any oxygen that's in there is also going to be part of the carbon dioxide or the water. So the gases then come out through a tube containing an H2O absorber. This is going to absorb all the H2O. So you weigh this tube before and after the analysis, and the difference in mass tells you the mass of water that was given off. And then after that, it goes through a CO2 absorber. And again, you can weigh this and find the mass of CO2 that was released. So what happens is they're going to give you a problem something like this. This one only has carbon and hydrogen, and they're going to give us the masses of carbon dioxide and water. This one is a little messier. So here we're given the mass of the sample. This has carbon, hydrogen, and oxygen. So here's the mass of CO2, and we can from that calculate the mass of carbon. That's the mass of carbon that was originally in the sample. From the mass of the H2O, we can calculate the mass of hydrogen. That's the mass of the hydrogen that was in the sample. And then for the oxygen, well, we pumped a whole bunch of oxygen in there, so we can't measure that directly. But we can take the original sample mass and subtract the carbon and hydrogen and find out how much oxygen was in there. Now you have the masses of your three elements, and you can do what we just did and find the empirical formula. Doesn't that sound like fun? No, it doesn't.